All right, everyone, taking a look at our homework for the weekend. It was worksheet number 11. See the answers for the first 7 questions up there now. We'll scroll down and see a few more here. 8 and 9. Let's go to the next page. We got 10, 11, and 12 there. Any issues with any of those questions on the worksheet? These all involved hand rules. In fact, specifically, the hand rule for deflection, which is used, of course, we spent a half an hour reviewing that one day last week, right? The 3 hand rules. We use the hand rule for deflection anytime you've got an external magnetic field, not the field that's caused by the particle, but an external magnetic field. And then, of course, you're trying to find the direction of the magnetic force on the particle that's moving through that external magnetic field. So for the first 6 questions, I believe it was, we were looking at the hand rule for deflection. And then after that, it was calculation type questions involving F is equal to QVB, which, remember, F is equal to QVB, the equation that you see up there for all 3 of those questions on the board right now, valid every time a charged particle is moving through a magnetic field if the particle is perpendicular to the field. If the particle is parallel to the field, what do we use to find the force? The quick, simple answer to that. What's the force if the particle is moving parallel to the field as opposed to perpendicular? 0. 0. Right? So in these questions, these 3 ones up on the board at least, it's perpendicular, so we use the equation QVB. If it's parallel, however, we don't need to worry about using any equation because the force is 0. If it's something in between perpendicular and parallel, then we're not going to worry about that because we're not going to see that in Physics 30. Questions? Yep. 4, 5, and 7. Okay. Any others? Okay, 4, 5, and 7 it is. Let's bring up the blank copy of it here now. And number 4 says an alpha particle. So right away we see that if it's in the context of magnetic fields, then we know we're going to have to use a hand rule, whatever hand rule it happens to be. And since it's an alpha particle, we're going to use our right hand rule. Our right hand rule. It's traveling to the north, which we're saying is geographic north, of course, which is actually magnetic south, right? If there were a magnetic field that points to the west, which way does the magnetic force point? So, listen, we know when we look out the window, we see the mountains to the west, right? And then, therefore, we know that that's geographic north up that way towards Calgary, towards Edmonton. And that's south, and that's to the east. So we can do that if we want. We could say, look, our right thumb points in the direction of the particle, which is towards geographic north, towards Edmonton. Fingers point in the direction of the field, which is towards the mountains, okay, towards the west, I think it was. Yeah, towards the west. My palm's going to point which way? Upwards. So we're not going to say out of the page here because our frame of reference is the Earth, north, south, east, west. So we're going to say upwards. If you wanted to say out of the Earth, you could do that, but upwards means the same thing as out of the Earth. Now, here's the thing. When you write your diploma exam, you're going to be in the cafeteria, and there's no windows there. So you're not going to be able to look out the window and get a visualization as to which way is north, south, east, west. So you're going to have to pick a north. Yeah, I don't know which way you'll be facing. You'll actually probably be facing the same way as you're facing right now, except you won't be able to look out the windows and see which way is north, south, east, west. So let's say we're not sure. When we look around us, we're not sure which way is actually north and which way is actually south. If that's the case, it's okay. Let's pretend the way you're looking is north. Pretend you don't see out the window right now. The way you're looking is north. If that's north, geographic north that is, then to your left would be what? West, east, and south. It doesn't matter if that's right. Okay, as long as you use your hand rule according to the frame of reference that you've defined in the room you're in. So when we did this question, we knew which way was north. It's that way. But if you can't see out the window, we won't necessarily know which way is north. That's okay. Okay, define your north, but just make sure you define your west and east and south relative to that correctly. So we'd say thumb in the direction of the particle, which is to the north, fingers in the direction of the field, which is to the west, right? Palm's going to still point upwards or out of the Earth. 5 was the next one. Okay, 5 says an electron travels to the north, there's a magnetic field. Okay, I'm going to circle that and put an LH for left hand to remind me that when I go to use a hand rule, it's going to be the left hand. Negative particle, left hand. So we got a particle traveling to the north. We got a magnetic field that's pointing to the north. Again, you can't see out the window here. That's going to be north for us. Particles traveling this way, magnetic field is this way. What's the force? What's the force on a particle when it's traveling parallel to the field? 0. So what's the direction of this force? It's 0. I don't know what the mathematical term for that would be, but undefined maybe? The bottom line is there is no force, so you can't really define a direction when there is no force. And 7 was the last one, really? 7 says, an electron traveling to the east experiences a magnetic force to the north. Which way is the field? So this is the algebra on the hand rule for deflection, right? Usually we're saying thumb, fingers, palm points, whichever way. This time we're saying thumb, palm, fingers point, whichever way. We got to find out which way those fingers point. It's an electron, so it's going to be a left-hand rule. We know it is going to be the hand rule for deflection again because we've got an external magnetic field, and although we're not trying to find the force, we have a force. We're given a force here. Which way does the magnetic field point? So, all right, so we're going to say the electron, so it's left hand, is traveling to the east. Can't see out the window. This way is north, south, east, and west. The electron is traveling towards the east, so we're going to stick our thumb this way, okay, towards the east. Our fingers, we don't know. Our palm is pointing, the magnetic force is to the north, this way. So we're going to say thumb to the east, palm to the north. Which way do your fingers point? Sorry? Upwards, yes, upwards. So out of the earth. Up or up, however you want to say that. Good. Any more questions on that worksheet? All right, we also did a little bit of stuff on Friday. We started it on Thursday, but spent a little bit more time with it on Friday. Talked specifically about the path of the charged particle as it goes through that external magnetic field, the path of the particle. Well, we know that the path of the particle is a circle, right? We did an analysis where the charged particle was going through the magnetic field. It experienced a force in a certain direction. But when it experienced that force, the direction of the particle also changed. So if the particle direction changes, then the force will change direction again. So the force constantly changes direction as the velocity constantly changes direction. That force is always directed toward the center, toward one point. And in the end, the path of that particle ends up being a circle. Since it's a circle with a force pointing toward the center, we're allowed to use the equation for centripetal force to describe it. F is equal to mv squared over r. Of course, we're still allowed to use F is equal to qvb. That hasn't changed. But we're also allowed to use Fc is equal to Fm. The two of these forces above equal to each other. Because in the end, if the magnetic force is what causes the force toward the center, and the force toward the center we define as the centripetal force, then the centripetal force will be equal to the magnetic force. Now, all this applies if the charged particle is moving perpendicular to the magnetic field. If it's parallel, there is no force. So it's not going to go in a circle. There's no force. If it's something other than perpendicular parallel, we're not going to worry about it. All right? We had one more question for homework, and that was the first question on worksheet number 12. The answer to that was 0.52 meters. Let's take a look at that anyways, whether you need it gone over or not, just as a little bit of a review as to A, how to rearrange that equation, B, how to plug numbers into it and solve for it. It says, what's the radius of curvature of an alpha particle? I don't know if anybody caught the poor wording of this question, but we're not actually looking for the radius of curvature of the alpha particle. We're looking for the radius of curvature of the alpha particle's path. We can't find the radius of an alpha particle, right? Anybody kind of notice that and think like, oh, that doesn't make sense? We know what we meant anyways, right? We know what I meant when I wrote this question. What's the radius of curvature of the alpha particle's path moving at this speed through a magnetic field of 1.0 times 10 negative 1 Tesla? Charged particle going through a magnetic field. We know it goes in a circle. We know that the three equations that we just wrote on the board apply. F is equal to QVB, F is equal to mv squared over r, and F is equal to, FC is equal to Fm. I told you guys this last week. If you're looking for radius, then odds are it's going to be this equation. It's the combination of them. FC is equal to Fm. If we find we plug our numbers in here and it doesn't work out for us, that's okay. We'll try one of the other two, either the FC equation or the Fm equation. Okay, you're not going to go wrong by doing this. I'm just saying that 95% of the time we're dealing with a question involving the radius of a charged particle in a magnetic field. This is what you're going to end up using. So let's start with that at least. Start with the thing with the highest probability. Okay, that gives us mv squared over r equals QVB. Anybody remember or figure out what the shortcut was there? It's a small one, but it's a little bit of a help. Daniel? Good. You can cancel out one of the v's. Okay. There's two v's on the left-hand side, one v on the right side. One of those v's disappears on each side. That leaves me with mv over r equals q times b. Now we're looking for r. So let's take the r up to the top. R has got to be on the top. Becomes mv equals qb times r, and then we're going to take the qb down by dividing. Becomes r is equal to mv over qb. My suggestion would be don't memorize this equation for r. We'll use it a lot. So you may think in a couple of days that, oh, I got it. I got it. I don't need to derive it every time because I remember this equation. R is equal to mv over qb. To this day, 20 years after I started teaching this stuff, I still don't memorize that form of that equation, even though I've used it literally thousands of times. Okay? If I tried to remember it, I probably would because I've used it so many times. Okay? But I don't try to remember it because when I try to remember something like this, okay, I got about a 50-50 chance of saying R is equal to mv over qb, and another 50-50 chance of saying R is equal to qb over mv. Okay? 50-50 chance isn't good enough for me. Okay, I want to get it right all the time. So I'm going to figure out this equation every time. It's an alpha particle. The mass is 6.65 times 10 to the minus 27. Got a speed of 2.5 times 10 to the 6. The charge is 3.2 times 10 to the minus 19. And the magnetic field strength is 0.10 Tesla. So let's figure this out on our calculators to make sure that we can do everything correctly. I've mentioned this before, but I'll mention it again. When you're putting scientific notation into a calculator, don't use this. Don't do this. Okay? Don't do this. Okay, that's a bad habit. You will find that when your numbers are on the top, that will work for you every time. Okay, but it's a bad habit because it won't work for you every time when your numbers are on the bottom. Let's do this. 6.65 second function EE neg 27. What that does is attaches the base and the exponent to the 6.65. Okay, it's not multiplying a number and a couple numbers multiplied together. Here we're actually physically putting the times 10 to the 27 with it, except it should be 10 to the negative 27, shouldn't it? Yeah, that's what I got actually. Let's multiply that by 2.5, second function EE 6. Let's press equals. Let's divide that by some brackets here. 3.2 EE neg 19 times 0.1, end the bracket. We get 0.5195 or 0.52 meters. How many people got that? Good. We're going to take a look at a couple multiple choice questions here. These are in your multiple choice booklet. We've done a question virtually identical to this before, but we'll do it again because it's appeared as a multiple choice question in the past. First one that I want you to do relates to the information that you see right there on the board. The first two questions, in fact, relate to that information. So I'd like you to do 75 and 76 relating to the information you just saw. I'd like you to submit those, please, as multiple choice number 1 and numerical response number 1, both on the same submission, please. Okay, put them both together. All right, so we got a variety of answers actually for question number 75. We've got protons in the solar wind experiencing a magnetic force. We actually did this question in class one day. We just did it as an example, and it was a hand-drawn diagram. But in the end, what hand rule do we use here? We want to find out which way these particles are deflected. Which hand rule do we use? Wire grasp, coil rule, or hand rule for deflection? Deflection rule, right? So we're going to use our right hand for deflection, thumb in the direction of the particle, which is to the right. At that point, my fingers are going to point upwards toward magnetic south there. So it's thumb, fingers upwards, palm's going to point out of the page. So the answer would be B for this one, out of the plane of the page. If you said into the plane of the page, you probably use your left hand. Okay, it's protons, so you got to use your right hand. Daniel? I'm sorry? When does what? Sorry? Why does the thumb go to the right? Because particles, Daniel, are protons, and they're moving. You can probably see this a little bit better on your paper, but you can see the protons are moving towards the right. So my thumb always points in the direction of the moving particles. Okay, and that's to the right there. So thumb to the right, fingers up toward the top of the page, palm points out of the page. Good? All right, and the second question, we want to find the radius of the circular path. Well, it's almost the same as that question number 1 on worksheet number 12 that we just did a minute ago, where we said FC is equal to FM. We're allowed to use either of the other two equations, but usually when we're looking for radius, this is the form that it's going to take. As Daniel said, one of these are going to cancel. I get MV over R equals Q times B. Rearrange that to solve for R. Becomes MV over Q times B. Okay, plug in the numbers there. And what do we end up getting there when we plug in the numbers into that equation? Keeping in mind that we're dealing with protons, so it's the mass of the proton, 1.67 times 10 to the minus 27, not the mass of the electron. Okay, it's probably a good idea, in fact, to circle protons when you see that, to remind you of that, because we seem to get in this habit of using the charge and the mass of the electron as opposed to the proton. What do we end up getting there? (7.59 times 10 to the 4). And how do we express that? Well, it's ABCD, so we'd express it as 7594. If it was B times 10 to the W, it would be 7.59. 7.59. All right. Here's another scenario that is the basis of some questions that I want you to do. Photon matter interactions. It says when a photon passes through matter. You know what? I'm going to let you guys read this yourself, okay? Rather than me read it for you. I'm going to let you read it yourself, but what I want to point out before we do that is just a couple of things, okay? First of all, a photon. You don't really need to know what a photon is. If you haven't heard of it before, it's probably not really going to be relevant. But I'll tell you that a photon is just a little particle of light. So just for context, a photon is a chunk of light, a particle of light, okay? We're talking about scattering. We mean it's going to bounce off in a certain direction, okay, one direction or another. One more term. Where is it here? The photoelectric effect. We'll also learn what that is later on, but basically the photoelectric effect is just a process. They actually describe it for us there, right? When a photon of light strikes something, sometimes an electron is ejected. Now, do you need to really know that at this point? No. So it's probably not going to be relevant at this point, okay? Don't lose any sleep over that stuff. Okay, read through this. Okay, see what looks like it might be relevant. Underline things or some highlights of some things or write some notes in. and then tackle the questions that go along with that, which are questions 77 and 78. Have you submit those as multiple choice number 1 and 2, please. All right, so let's go back to the question, or the stem of the question here now. It describes this photon matter interactions, and we talked about a photon. We talked about what that is. It's a particle of light. When it interacts with matter, this is what can happen. Okay, the photon could be scattered, or the photon could reflect off somewhere and lose some energy in the process. We call that the Compton effect. Okay, which you will learn about in our last unit of Physics 30 towards the end of the year, December and January. The photon may move an electron out of the atom, and in the process, the photon disappears. So the photon's gone now, but an electron has been ejected instead. And we call that the photoelectric effect, which we'll also learn about here before too awful long here. The photon may move an electron to a higher energy state in the atom, and in the process, the photon disappears. So the photon is absorbed, and the electron jumps to a higher level. You may have learned about that a little bit in chemistry class. We'll learn about it more in physics as the year goes on, but again, it doesn't really matter. Okay, it doesn't really matter to the question at hand. The photon may actually create matter. The most common process is called pair production, where an electron and a positron, whatever that is, okay, ends up being the antiparticle of an electron. Okay, when they hit each other, they annihilate. What happens is we end up producing this. Sorry here. Sorry, when a proton, it's not an electron and a positron hitting each other, because when that happens, they do annihilate and produce pure energy. But when we've got this photon, this energy, the opposite process can take place, which means that instead of creating energy from matter and antimatter, we can actually create matter and antimatter from energy. So in this process called pair production, you've got this photon, and you end up producing an electron and a positron. So here's where the electron, here's what happens. You get the photon down here, which is just light, and then you get a positron, which is a positive particle right there, and an electron, which is a negative particle right there, being curved or being deflected by an external magnetic field. We want to know now, which way the magnetic field has to point in order to cause the positron and the electron to deflect the way that they do. There's one answer to this question. So it doesn't matter whether you're dealing with a positron or the electron, the magnetic field has to point the same way. Okay, and that should make sense to us a little bit at least. If we've got a negative particle, a magnetic field pointing one way will cause it to deflect a certain way. A positive particle will be deflected opposite to that. So there's no conflict here. The positive particle is being deflected up, the negative particle downward, no big deal. Okay, what we're going to do now is pick a particle, either positive or negative. What I'm going to do is pick the negative because habit. Right? I'm going to stick my thumb in the direction of the particle, which is originally to the right. Before it's deflected, the particle is moving to the right. There's a magnetic force downward on it. Otherwise, it wouldn't deflect downward. So it's thumb to the right, thumb to the right, palm pointing downward. Fingers are going to point which way? Into the page. So the magnetic field would be into the page. If we were dealing with the positron, we can do that if you want. We'd use our right hand. It would be the right thumb in the direction of the particle. This time the force would be upwards because the positron is deflected upwards. In the end, my fingers are still pointing into the page. So any way you look at it, the magnetic field is into the page, and the answer for that one would be A. What's the speed of the particle in a circular path? Certain radius? Well, all we're doing is deriving an equation there that we've done before. Fc is equal to Fm, mv squared over r equals qvb. As Daniel said earlier on, one of the v's cancels out. Let's solve for v now. Take the r up by multiplying, qbr. Take the m down by dividing, qbr over m. The answer becomes A, bqr over m. Now, there's two more questions that I'd like you to do here. We're not going to have you submit these ones just in the interest of time. Just do these ones at your desk, and in about 3 minutes or less, we'll do them as a class here, okay? All right, let's take a look here, guys. If you're anything like me on this question, you end up trying the wrong thing first, okay? Because that's what I did the first time I saw this question. I tried the wrong thing. So there's a proton with an energy of 894 electron volts. That's a little bit different. Okay, we know that we're usually in joules and we want to be in joules. Okay, if we need that, we'll convert it later on. Goes through a circular path with a radius of 3.6 times 10 to the minus 4. We want to find the speed of the proton. Okay, tell me, put up your hand if you tried this first. Fc is equal to Fm. How many people tried that first? Okay, I did. The first time I did this question, that's what I did. Okay, but it doesn't give me an answer. It's not wrong. I told you it's okay to try that. Okay, worst case scenario is it doesn't work for you. And it doesn't work for you here because you don't know what V is. You don't know what the speed is. You're looking for that. And there's something else you don't know either. The magnetic field strength, you don't know either. So there ends up being two unknowns in that equation there. So let's try something else. F is equal to QVB. No, that doesn't work. F is equal to mv squared over r. No, that doesn't work. What else do you see that we could try there? Yep. Yeah, we got an energy. Look, we got an energy of a particle is 894 electron volts. We want to find the speed. Let's just say EK is equal to 1 FmV squared. Becomes 2 EK over m. We just got to make sure that we convert that 894 electron volts to joules. We say 1 electron volt is 1.6 times 10 to the minus 19 joules equals 894 electron volts over x joules. So let's get a value for x, okay, in joules. Let's plug it into here. Let's divide it by the mass of the proton, square root it, and when we do that, we should get an answer. I'm guessing that's A, then it being A, 4.14 times 10 to the 5. I knew C and D were going to be wrong because they were both faster than the speed of light. So I knew it was going to have to be either A or B, and usually the speed of something like this is in the range of 10 to the 5, 10 to the 6. So if I was going to guess, I was going to guess 10 to the 5. Now, 81 says the strength of the magnetic field. We're looking for the strength of the magnetic field. This is when I'm like, oh, okay, wait. That's when I do what I want to do. Okay, I wanted to do Fc is equal to Fm. Let's try that now. Let's say mv squared over r equals qv. V cancels. We're left with mv over r equals q times v. This time we're solving for b for the first time. Ends up being equal to mv over q times r. So let's plug our numbers in there. Again, make sure you use the data for a proton, not for an electron. Okay, and we get our value for that. What do we end up getting there, Emma? Ten to the 1.20 times 10 to the 1, which is working for the values of A, B, C, D. We'd say 1201. If it was B times 10 to the W, it would be 1.20. Done. We're going to do one more here, guys, and that'll pretty much wrap it up for us here, okay? We'll do this one as a group, though, right off the top, okay? This one says a proton enters the magnetic field at a right angle to the field. Hey, right angles are good. Okay, we know what to do when we have right angles. We know the hand rule applies. The hand rule for deflection applies. We know the equations that we've learned. Fc, Fm, Fc equals Fm. We know all that stuff applies. The alpha particle enters the same field at the same angle, but at twice the speed. We want to know what the radius of the path of the alpha particle as compared to the radius of the path of the proton's particle. So we're looking for a ratio between the two. Okay, the word ratio means the same thing as the word compare, and the word compare means divide. So every time you see a question where you're looking for a ratio, every time you see a question where you're looking to compare, I want you to divide two numbers. The ratio of the radius of the alpha particle's path to the proton's path, let's divide the radius of the alpha particle's path by the radius of the proton's path. Now, if we knew the numbers for both of those, then that'd be great. All we'd have to do is divide them, we'd be done. But we don't. So let's put in expressions for them. The radius of the alpha particle's path is mv over qb. Okay, we derived that equation several times here, right, from Fc equals Fm. But we got to be careful to use some subscripts here. 1 second here, guys. Use some subscripts. The mass of the alpha particle, velocity of the alpha particle, charge of the alpha particle, magnetic field strength is just the magnetic field strength. Proton, same thing. M proton, V proton, Q proton, B. The B cancels because it's the same magnetic field. You got the value for M and Q. Now, here's the trick, though. we need a value for speed. We don't know what either of the speeds are, but we do know that the speed of the alpha particle is twice the speed of the proton. So let's say m alpha 2v proton over q alpha over m proton v proton over q proton. V proton cancels, and I'm left with this number, which I can plug in, times 2 over this number, which I can plug in, get a number. I can't remember what it works out to be. Let's say it's 4. Okay, I don't know if it's 4 or not. Let's say it's 4. Okay, what's my answer? It would be C, right? 4 to 1 ratio. Does that make sense? All right.